burst imaging captures multiple frames in rapid succession, then aligns and fuses them into a high-quality image. It is especially effective in low-light scenes with severe noise. Recent advancements in burst image restoration primarily focus on improving alignment and fusion algorithms. These methods improve burst restoration by better aligning and fusing features across the input burst frames. However, one crucial aspect of burst imaging has been largely overlooked: finding the optimal exposure settings, such as ISO and exposure time, for burst images. Most methods assume uniform exposure settings, where all burst frames are captured with the same exposure. As a result, the frames have similar noise and blur levels, limiting their complementary information. In contrast, most non-uniform exposure methods target HDR imaging. For restoration, dual exposure methods capture to frames with short and long exposures, and use their complementary information. However, their performance is limited by the fixed number of input frames. Recently, a method using predefined non-uniform exposure sequences has been proposed for denoising, deblurring, and HDR imaging. However, it still relies on fixed exposure settings, regardless of the real-time capture condition. Auto-exposure methods adjust exposure settings for real-time capture, but most focus only on proper brightness. For restoration, this method predicts exposure time using preview-based motion metering. However, it assumes a uniform exposure time for all burst frames, and does not consider the downstream restoration algorithm when selecting the exposure. In summary, previous methods rely on manually designed or uniform exposure settings, and do not consider the restoration network. We propose an effective pipeline for burst image restoration. Given the latest preview image, its gain value, and scene motion estimated from two preview images, our pipeline restores a single denoised and deblurred image. During training, BAENet first takes these inputs and predicts the exposure time for each burst frame. Then, a differentiable burst simulator synthesizes the burst images for the predicted exposure times, and the restoration network reconstructs the final image. However, training BAENet is challenging because ground truth exposure times are not available. Finding the optimal exposure times for a scene would require comparing countless burst combinations captured with different exposure settings, which is impractical. To address this, we introduce a differentiable burst simulator, an effective training strategy for BAENet. Given exposure times, the simulator synthesizes realistic burst images with noise and blur, while keeping the entire process differentiable. This allows BAENet to be trained directly with the restoration loss, without requiring ground truth exposure times. At inference time, the burst simulator is removed. BAENet predicts the exposure times, and a real camera captures burst images accordingly for restoration. On our synthetic test set, DEBIR consistently outperforms representative exposure strategies in burst image restoration. Qualitative results also show that DEBIR produces sharper and clearer images. In the real camera experiment, DEBIR produces a cleaner and sharper image than exposure bracketing, with better no-reference image quality scores. Here, we analyze the exposure patterns predicted by BAENet. BAENet adjusts exposure times based on motion and preview gain to reduce blur and noise. It also assigns complementary exposures to adjacent burst frames for better restoration. Here is a brief summary of our work. Thank you for listening. Please follow our project page for more details.